So what we want to highlight here is ML lifecycle for any real life project is not different from any data science. So what we need to typically understand is the life cycle is more important than actual technique of deep learning or machine learning which is actually used in practice. So if you see broadly, if you find of looking at understanding the core business objective for your target application is becoming more important. What is the corresponding target application you're talking about? Converting that into a target ML problem is most important. Are you looking at creating a better predictor? Are you looking at creating a better classifier? Or are you trying to create some kind of pattern extractor from your data? That is the question you have to ask. That becomes your business problem formulation, right? So you have to formulate the problem in form of classification, regression, network analysis, or clustering, or recommendation system. That is basically what you need to understand in terms of business problem formulation. Then comes the notion of data preparation. Data preparation is usually the most complex and you can say the most time-taking scenario part of ML, where you look at the raw data that is coming in. You may get raw data with respect to a name, ID, some age, some consumption, volume, etc., etc. A lot of data actually may not be relevant for you. So you need to look at several techniques for filtering unwanted data from your original data because they may not add value to your final ML problem formulation. Second, you may need to look at optimizing the original data by reducing the dimensionality of data by removing unwanted data which is not making sense. So dimensionality reduction can be handled by several techniques. It could be by first looking at are there redundant columns, means which are too much gap, which are very little data, with too much missing values. Is there dependence within different variables? Then you can do a multi-collinearity test and remove multiple variables and replace them with smaller number of variables. Then you can actually do a dimensionality reduction by using an unsupervised technique called principal component analysis, whereby you take the original data, combine them one after another in terms of some combination so that you have much reduced number of dimensions. In fact, I have seen scenarios where you can reduce from 100 dimensions down to even 10 dimensions for the final principal components, which is used for the final target problem. So what happens in dimensionality reduction is you typically will want to look at not just the original input variables as is, but transform components like principal components and use the principal components as the problem for your target ML problem. Now that you have a prepared data, now you start to look at, okay, now I have data prepared for my ML. Now what you can do is you can actually run a loop within here of model building and model evaluation. And this can be a continuous loop. By that I mean, once you have the problem formulated, here you will try to identify, depending upon the problem, suppose you decide there is a classification problem. Then you can run multiple algorithms here with different hyperparameters or different parameters. You can run Bayesian tree, you can run logical regression, or you can run multi-layer perceptron, or you can run a simple naive-based classifier, or different kinds of classification techniques you can run on the data. And then for each one, you can try to find out what is the corresponding accuracy or sensitivity or AUC under the ROC curve, and then see if it satisfies your need. And then among all the possible results, you may try to choose the best model and go on deploy it. Once you deploy, you're only worried about binary model which you have saved as the best model out of all the models you've tried across different variations of the algorithm. So, in order for us to understand the best model, you need to understand what are the model evaluation parameters for each parameter. And also you need to understand for model building, a key element is what are the hyperparameters on which you need to change. So, to give an example, let's say we're talking about random forest. In random forest, you can have two kinds of parameters. One is number of trees, say 200, 250. Then you can also say, what should be the basis of my Bayesian tree formulation in the random forest? Like, do you want to use Gini or do you want to use entropy? Do you want to give something like, maximum number of levels you allow in the tree? Most programming language allows you different formulations for parameters for each parameter, for each algorithm. So, the task of ML programmer or the data scientist becomes how you can vary the different train test combinations of data from your original data and run different variations of the same algorithm with different parameters and compute accuracies and different models, evaluate metrics, form a comprehensive table and then choose the best after discussing with the domain expert. And once you choose the best, you remember what was the hyperparameter combination and what was the train test split combination which was used, and that becomes the choice of the model for deployment. Then you take binary version of the model. It may be the decision tree which you created or the random forest, which is the collection of trees which you created. That becomes the source for deployment. And then you put it into the target system. When you put in your target system for deployment, here you may want to do things like sizing. Suppose you are expecting suppose you created a fraud detection algorithm, and fraud detection is in form of a random forest classifier out there, and it flags whether something is fraud or not. It's part of, say, network traffic that is coming, which constantly is a web application which uses this and which returns yes or no. And then what happens is if it requires millions of hits per second, then probably you would use a big data infrastructure like a Hadoop or a Spark to actually go and host the corresponding binary model and work on it. So then this becomes the final deployed application using the target model which you have generated as a result of the entire ML lifecycle. So if you see, ML lifecycle is mostly dependent upon the entire 9 yards of understanding the problem, formulating the problem, preparing the data, cleaning the data, like for example, filtering may also involve removing things like null values, imputing values. Namesh-type reduction may involve things like principal components. Then making them ready for model evaluation by iterating across different machine learning algorithms. Then we pass it to the model evaluation phase based on each model requiring different parameters. So classifier may need accuracy, sensitivity, precision, recall, F-score. In case of clustering, you may require looking at what is the potential spread across clusters. Or in case of regression, you may look at R square. So depending upon the measure, you look at the corresponding valuation metric, and then you may choose the best possible combination of hyperparameters across the different learning mechanisms, choose the deployable model, go and deploy it in the target system which you want to use it, and then depending upon the sizing of the requirement, you may want to deploy a corresponding big data infrastructure to go and deploy the ML. So it's important for us to consider that we do not want to restrict our ML to be only this model building phase, which is very glamorous because this involves a lot of machine learning algorithms to be practiced in data, but a significant amount of work goes in data preparation and business problem formulation, and also in terms of deployment, where you want to deploy the target model once you declare that as the model which you want to streamline and finalize a baseline as the model for deployment. Again, at the long run, it is also possible that you have to revisit to the business problem formulation itself. The underlying truth in the data has changed because of the change in the business behavior, etc. Then you have to go back to the drawing board and maybe here, or you may have to go back to here to reformulate the problem itself and regenerate the model. Then you have to replace the model once it's generated and replace with a newer model that is deployed. So what happens is, this is a continuous cycle. There is no concept like this is one time done and deployed. So you have to constantly iterate depending upon the truth of the business, changing and models also not reflecting the latest truth. So frequency of change will be different. For retail, it may be every quarter. For stock market, it may be every day. For insurance, it may be yearly. So it depends on the frequency of change. Is entirely dependent on the target business in which we talk about. So it's important for us to understand that ML lifecycle is a whole 9 yards, involves importance attached to every stage. And this is very similar to what we do in data science or any software engineering lifecycle. So in that sense, ML is not very different from a typical software engineering lifecycle.